So today we want to look at network problem. A network is a connection of parts, arcs, branches is the same word, with nodes, where items are moved from one node to another node. A node is like a junction where several items pass by, either cars or items or human beings, anything. And a network diagram is very powerful because you can use it to do a lot of things. Nodes are like junctions. Suppose you are going to Accra from Medina. Who can tell me some of the nodes along the way from Medina to Accra? What are some of the nodes? Raise your hand, please, and tell me some of the nodes. Deborah.
37.
37. What else? What are some of the nodes? There's something about the node that when you mention, I'll query you. Belinda. Shiashi. Daniel.
Water old overhead.
Who?
At water old overhead.
To be honest, Shiashi is not really a node. The best of a node is not really Shiashi, but what? Akolache.
Atomic junction.
What?
Atomic junction.
Atomic junction, that's it. Atomic junction is a clear node. But there's also another one, Kelvin.
Service Legon junction.
Exactly. Legonokbongolo is a clear node. Kletos, you have said your own.
Not yet, Prof. Akwaje interchange.
Akwaje interchange is a clear node. Is that where Opebia house is?
No, sir.
No, sir. Right after Jubilee House.
Okay, yeah, you have left, right, and front, right? So for it to be
Yes,
a
Prof.
node, it has to be left, right, and front. That is why she cannot be a clear node. But Accra Mall Junction can be a clear node because you have the motorway, front, left, right. A node is represented in linear programming as a circle. Yes, Joseph. A node is represented as a circle. A decision variable is represented as an arc. So the arc, we represent it using the decision variable. And then the constraint, so the node, which is also the constraint, is represented by, the node is represented by a constraint. A graph will help you to better understand this node, but there are several of them. So look on your screen there. How many nodes do we have? How many nodes do we have? Yasmin.
Five.
How many?
Five nodes.
How many? Good. How many constraints do we have? Who can tell us? How many constraints do we have? Calvin.
5.
5, wrong. Next person. Samuelata.
Talk 7.
7. So the decision variables are 7. They are represented by the arc. The constraints are 5. They are represented by the nodes. They are demand nodes. They are the ones that receive the items. And they are supply nodes. They are the ones that move the items. So the supply nodes are sometimes called the going out arcs. The demand nodes are known as the coming in arcs. The sending nodes are the supply nodes. The receiving nodes are the demand nodes. You should be writing all of this, by the way. Now, we are going to take an integer programming. Because of the nature of the decision variable, unlike the normal linear programming, you see, the decision variable is defined as an item, the number of items transported from the supply node to a demand node, or basically the number of items transported from node I to node J. From node I to node J. And so the decision variable is not written as x2 or x1. No, it's represented as x12, x21, x13, x, because the 1, 2, 1, 3, 1, 4, those ones represent the sending node and the receiving node. Take note. I said it the last time. It is based on your questions. That is when I pause. Yes, sir.
Please, can you take the decision variable again? You said it is when like the items are going in and out. I wanted to get that correctly.
I said that a decision variable is not really the number of things you are producing as in normal linear programming. Normal linear programming, you have x1, x2, x3, because there is no connection between the items. But in network model, it is x12, x13, x21, and so forth. And the reason is because we are looking at items or products from one section to another. So the 1, 2 is not referring to the product, but it's referring to where it is from and where it is going. Does that make sense?
Yes, please. Thank you.
And we shall give an example very soon to picture the point. So to capture all of this, what our goal is that we are going to have a coefficient, let's say a cost or a distance, multiplying the decision variable xij, that is an item from node I to node j, or the items from Accra to Kumasi, or the items from Somanya to Hawaii. Once we got a cost or the distance represented by C, multiplying the items, we can sum all of them to create the decision variable. Okay, remember this and don't forget, write it down if you can. Arcs are the decision variables, the nodes are the constraints. Let's take some 3 special cases of linear programming that adopts transportation, transshipment, and assignment. In transportation, we are transporting something from the source, that is a supply, to the destination, that is a demand, at a minimum cost or at a minimum distance. The supply is fixed, the demand is fixed, and there's a cost, a variable cost associated with sending the items. When all the constraints are equal, okay, when the supply is equal to the demand, the total supply is equal to the total demand, we have a balanced transportation model. So a balanced transportation model is where, let's say that you are moving items from Accra to Kumasi, Accra to Takoradi, Accra to Hawaii, and you are also moving items from Pokwasi to Kumasi, Pokwasi to, and things like that, just as you did for Accra. The Accra and the Pokwasi here are the supply. And the total number of items from Accra and Kumasi, if it is combined together, and the total number of items are 400. And the total number of items being received at the other 3 stations combined together is also 400. Then we have a balanced transportation model. But if one is less, if the supply is less or the demand is less, then we have an unbalanced transportation model. Why is this important? Because the way you treat them in the model is different. And we shall look at an example. Okay, when you have constraints, when you have a balanced transportation model, all the constraints will take equal to sign. Take note. A balanced transportation model, all the constraints will have equality sign. But on balanced transportation model, some of the constraints will have equality. Some will have less than or equal to. So you will see an example of this. This is a general notation, general minimization problem, okay, and the constraints that one can have right there. Let's take a practical example. You see the way I quickly brushed through the model. I didn't want somebody to collapse. Okay, but some people, when they see some of these things, they think it's like Hebrew, you know. So I decided to quickly move away from that so that we look at the substantive point. Let's look at wheat, maize or wheat. They are harvested in the Midwest. They are stored in the grain elevators in three cities: Kansas, Omaha, and DM. So remember that you harvest wheat, you keep them in grain elevators. Okay, you keep them in grain elevators. And these grain elevators, they will supply 3 flour mills. They will supply mills. Mills is like Nika Nika, where you send the things to. And these mills are located in Chicago, St. Louis, and Cincinnati. Now, let's look at the items. Remember, we have elevators sending the things to the mills. From elevators in the 3 cities to the mills in the 3 cities. So as an example, you have Kansas City is supplying 150 tons of wheat. And it's going to supply it to all these 3 cities. Omaha is supplying 175 tons of wheat. It's also going to supply it to all these 3 cities. And DM is supplying the 275 tons of wheat to all the 3 cities. But then Chicago is not receiving exactly what Kansas City is supplying. Chicago is looking for 200 tons. St. Louis is looking for 100 tons. Cincinnati is looking for 300 tons. The amount associated with sending, I've used A, B, C, D here, but I'll change it to 4, 5, 6 so that everything will be in numerical form. So watch this $6. This $6 is the cost of transporting the items from Kansas to the first city, which is Chicago. $8 is the cost of transporting from Kansas to St. Louis. $10 is from Kansas to Cincinnati. Now, when it comes to Omaha, Omaha is costing us $7 to go to Chicago and $11 each to go to St. Louis and Cincinnati. And the same can be said of DM. First question is to define the decision variables for this transportation problem. Define the decision variables. Now, how do you define decision variables in a transportation problem? This is how you do it. You will always say that let Xij, Yasin.
I thought you were asking us to define, so I was going to try, but I just saw that you are explaining. So
Go ahead.
sorry.
Go ahead.
Oh, I was going to say let X1, X4 be the cost, like the cost to transport from, I think, Kansas to the first city, and then to follow that order.
Okay, the challenge with this, trying to mention all the names, is that you have a lot to write. The permutations are too many. So you say that let Xij be the number of items, write it down, everybody, transported. The number of items transported. And here there are 2 ways of writing that. The next one, transported from node I to node J. Node I to node J. And instead of from node I to node J, you will now be specific now and say from elevator I to, who can tell me the next one? From elevator I to Stanley.
Mail.
The
Mail
mail.
J.
Okay. Elevator I to mail J. That's how you do it. If you can write this beautifully, you're entitled to 4 marks. Who is not clear? Defining the decision variable is very important. Yes, Nassim.
No, please, can you go over again?
Please, can I ask my question or you go over?
Ask your question.
I was going to say for this decision variable, would you repeat it for all the like the remaining cities, or it's just the first one that
No, you only do it one. After you are done, you will now say that where I is equal to 1 to 3 and J is equal to 4 to 6. You see, the J here represents the other 3 cities where the 10 is going to, whereas the I represent the first one. Once you say this, it will capture everything. You don't need to say for each one again. Kofi?
So if I'm following you correctly, does that mean that J is actually, because I think it was A to B, A to C?
Yes, and I just mentioned that it's always best to use one numerical numbers to label them than letters.
Okay. Got it.
Yeah.
Following.
And you'll see that very soon. Stanley. Stanley,
Yes,
you have
sir.
this.
Okay, sir. I wanted to ask if is it possible that since maybe I'm going to write this decision variables, I can quote it somewhere and say I or 1 is this maybe St. Louis, 2 is this before I start with this, or it doesn't matter.
Oh, no, it doesn't really matter because you have indicated the node and we are going to show the node anyway. You show it in a graph.
Okay.
You see, the next question is to draw a graph, so there's no need.
Okay.
Yasin.
and please, you see, before the first thing you did was let xij be then number of items transported from node I to node J. That statement, is it always like supposed to be there? Because I realized that after that statement we were a bit more specific that from elevator I to node J. So the first statement, is it like always a requirement to put it there before you go
No.
ahead?
I mean, you can use that or you can use the next one, which is specific. Either one is fine.
Oh, okay. Thank you.
You got it. Yeah. Because in fact, that one, the first one is better because later on you come to know that when we add transshipment nodes, and then they are quite different transshipment, it can be confusing. So it's always good to keep it simple, node I to node J. That's it. But you have to indicate how many are the I's and how many are the J's. Okay. Now, we are now ready to draw the model before we formulate the model. So how do you do the drawing of this? Well, to do the drawing, you need the information. So let's go back to check the information at hand. So here we have the items, and then here we have the cost. I rather want to use where the cost is to bring home the point. Let me see if I can share a bigger screen instead of this very one. Share a bigger screen and use the board. All right. I'm sure you guys can see the screen. So we are going to deal with, the first thing we're going to be doing is do the nodes. Oh, people are writing. Look at that. How do I stop that? Okay. So you have, how do I even stop?
Doc, please, for people to not write, they are supposed to change the pencil and select the cursor so that only you would have access to the pencil.
Oh, you think these people will do? Don't do. Let's try and see. So you write the first node. Okay. Let me just undo this. And I use. So the first node is, so how many nodes are we going to write? You can tell us. How many nodes? What I'm writing here are the demand, the supply nodes. The supply nodes. How many are these nodes that I'm supposed to write? Yes, Yasin.
This is it two. Sorry, three.
How many?
Three.
Now, in all, I'm not supposed to write three.
No, then six, if you include the cost.
It's not a cost that I'm also talking about.
Okay.
Evans.
Bro, actually, I was also going to mention 6.
All right, no problem. So you're supposed to have 6. Oh, you're supposed to have 6 constraints. Okay. Because you're supposed to write 6 notes. And after that, you label them. 1, you should be doing this on your book. Whilst I'm doing 1, 2, 3, 4, 5, 6. Okay. So we are now going to look at the first one. Where is it? The first one. Yes, Yasin.
Please, just to confirm, on what basis did you write this the 6 notes? Is it with the supply and the demand side?
Okay, hold on. I'll show you.
Okay.
So if you look at this cost, the cost in all of them, okay, and then you have here, normally you look at both the demand and the supply. Both the demand and then the supply. That's it. And the total, if you look at the demand, there are how many? Supply, there are 3 of them. And then demand, there are 3 of them. So that tells you that the number of constraints you're going to have is 3. Does that answer your question?
You just said that means the
Sorry, the
number of
number of constraints you're going to have is 6.
Okay, then it does.
Right.
Thank you.
So now you're going to document clearly. Hey, where is this thing? Looks like I need to go back all the time. You're going to indicate clearly I hope that this thing will just let me continue because it likes taking it's like every time you got to go back. Okay, let's see this. Why do I have to always reload like this? Okay, so now you have to now draw the axe. And the way you draw the axe is that pick each supply node and move it all the way to the demand node. Okay, pick each supply node and move it to the demand node. By the way, after you have written the supply and then the demand, you should indicate the amount of supply. So if you look at the first one is Kansas City, which is number 1, and then the supply there for Kansas City is, if you check, it is 150. 150. Okay. So now you write 150 here. Then the next one is, if you check, it's 175. So you write 175 attached to Omaha. And then 275 attached to DM. And then you go to the right side. The first one is Chicago, and that is 200. St. Louis is 100, and Cincinnati is 300. You now put the total supply on the far left. If you check total supply, 600. And then the total supply demand is also 600. You write it nicely there. Now we are ready to draw the axe. And each time you draw the axe, you show it. So let's take, for example, the first one. You draw with the axe with arrows. So I'm going to start with this one and move an arrow to there. Okay. Now, how do you, after you've done that, you should label it immediately. And the way you label it is check the cost. And when you check the cost, you will see that from Kansas City to the first one, Chicago, is $6. But you have to write the decision variable first. So you write X14. That means it's from node 1 going to node 4. And then the cost, which is $6, you write it at the far right. Then you come to the next one. Okay. So you go to the next one. Yes, indeed.
Please, when you're writing the decision variables, like, is it recommended to put comma? Because you see, when you do X14, someone can read it
There's
as
no comma. It's
X14.
all together.
Okay. Thank you.
Yeah, it's all together. So you now document the second one, which is from node 1 to node 2. Okay. And then you do from node 1 to node 3. Let me just write it before I come to it. So node 1 to node 2, the question is, what is it? If you check it as it stands now, it's going to be X what? Anybody? It's going to be X what?
X15.
X15. Okay. And when you check the associated cost, that was $8. So it's going to be
Yes.
$8 here. And then the last one is going to be X16. And the cost associated there is $10. That is how you do it. But you have just done for number 1. You see, if you do all the drawings, the arc drawing, if you do all the arc drawing and you tell it, you are now going to label them, it's not going to be good.
How much is this?
You are going to struggle. You cannot even track it. Okay. So what you have to do,
By 2.
who is talking plenty like that? You don't mean, let me mute everybody. If you have a question, then you raise your hand, because some people simply don't help us at all. They just don't know that they are supposed to be silent in an environment of peace. So now I need to go back and then. So once you identify this, you write it, you draw the arc, you write, you draw the arc, you write, okay? And then you do that for all of the rest. You've got to learn how to write this. What I'm showing you here is just 6 nodes. If you check some of the past questions, you see some of them are even 40 nodes, 30 nodes, 28 nodes, 33 nodes, and all that. So it's very important that you label it immediately you draw. Otherwise, a better when you so. All right. The next thing you got to do now, and so if you should do this very well, this is what you're going to experience. Yes. Yeah, Ashla.
Okay, please, I get the bit of node 1 to 4, but please, if you can clarify why we are doing node 1 to 5 and node 1 to 6.
No, one of the things is that you got to do for everyone. When you are doing the node, you have to do from 1 going to all of them. You have to do from 2 going to all of them. And you have to do from 3 going to all of them. You are not doing for only one. You're doing for all of them. Because as it stands, you don't know where to send it to. For example, if you start from Kansas City, you don't know where you're going. You're going to go to another place depending on the cost. And right now, as it stands, it looks to you that the cost is what, $6 here, $8 here, $10 here. So you will go here. But the question is that even if you go here, even if you take all the 150 from Kansas City to here, that is not what this guy is looking for. That is not what Chicago is looking for. Chicago is expecting 200 items, and you have brought only 150. So you got to distribute the whole thing in such a way that your total net, your net cost is minimized, not one particular cost is minimized. And that is why you got to take into consideration all others. So you got to move the app to all others. I'm about to show you when I've done all. So if you go to the next one, if I were to continue the next one, I'll take these two, go here, these two come here, these two come here. Then I'll go this one here, this one there, this one there. So all of them will have to go. So that's why I'm saying that when the nodes are many, you will see that you have to do a lot of line drawings. Okay. You see, at this stage, if you don't take it, you don't even know which one is going anywhere. So you have to track them. Does that answer your question? Yeah, you asked me.
Please, as a follow-up to the question she asked, right? Are we also sending it to all the nodes because the question said that like from each city it goes to the 3 different mills, or is it that in every like it depends on the question?
It doesn't. It's always going to go everywhere.
Okay.
You are looking at this from a whole bunch of warehouse company, a particular company is going everywhere. So, okay. So once you've done this, let's now show the complete. So when you look at this very one, okay, let me show you the example that we just did. This is the one I just did. And now you can see that I've incorporated all the others here. Remember that the labeling matters. Now, in this very example, I've used ABC, but ABC is not good. Always stick to the numbers. Okay. Now, at this stage, we are ready. If you're able to do this correctly, you get 7/7 for the drawing. Next one. We have to go forward and now formulate the objective function. And when you're formulating the objective function, your eye should look at the graph, nothing else. Your eye should look at the graph and nothing else. Okay. So we have a question from Flu. Go ahead, Flu. Or you've lowered your hand there. Okay. Go ahead.
Yes, sir. I was trying to unmute. I realized that on the one you did the total demand and the total supply, but it's not here. Are we to include it when we are doing it?
Yeah, include it. You can write it on top of your actual question, or you can put it on the graph. So here I did it, but I didn't put it on the graph. But it's always nice to add it to the graph so that it becomes easier.
Okay. And then also in your submission, you are using a couple of colors for the lines. In our writing, will be limited.
No, you don't need colors, as long as you can track them.
Okay, sure.
Yasin. Ben. And Belinda, any one of you can ask a question.
Sir, please, I wanted to know, since it's a minimization problem, we are trying to minimize transportation costs, or we are trying to minimize cost. Why are we like supplying to all these cities? Is it that we don't know how much Chicago demands. I'm just trying to understand why we have to supply to all these cities.
Why we have to supply them? So you have a warehouse where you always supply items from where you have produced to your warehouse. China does a lot of supply to countries. You have them. But then you have an aeroplane and you want to actually use that aeroplane to do the supply. But you want to be sure that you will cut down cost. And so you want to put the total cost, not one cost. You are going to supply to Ghana, you're going to supply to Nigeria, you're going to supply to this. Okay. You want to know the associated costs and minimize the cost. In fact, when you come and check, based on some costs, you will come to realize that for this particular year, you don't have to supply to this country. For that year, you don't. Some of the years will have maybe wars, earthquake, flood, typhoons, a tsunami. So many things will require you not to supply to that place. Sometimes there's cost associated with it. It will not help you to minimize the overall cost. Sometimes that particular place, their cost alone, maybe there is war, that cost alone will not allow you to minimize overall total cost. So you want to blend things in such a way that your overall total cost is minimized. And that is why you got to consider all of them. It's not like you don't know what they demanded. You know what they demanded, but you also want to send the items because the items are from places to places. Don't forget, you are not shipping them all the way from China to, you are sending it from South Africa to that, but it's yours. You're sending it across board. And so you want a good distance, a cheaper cost, okay, to be able to deliver. The Uber drivers, they do these things all the time. Sometimes the Uber driver will look at the thing and he will cancel the trip. Because when he looks at the cost of that movement and the return and everything, he realizes that it's not useful actually to go further and do anything. All right, let's go to Augustine.
Okay, so yeah, good afternoon. I've seen that. Is there a situation you can move from Omaha to Chicago before coming to St. Louis?
My question to you is that would that make practical cost sense? Would that make practical cost sense?
Yes, so I think because you're looking at destination and there may be other factors.
Of course, there may be other factors. There is a possibility, but that possibility might not. You see, they are all suppliers. Watch it. The moment you say that, it is possible, but the moment you say that, is there a possibility to move from Omaha to Chicago before you come to St. Louis? Then Chicago is no longer what? A destination. It's no longer demanding. It's a transit, and we call it transshipment. Because what you are saying is like, I'm moving the thing from Chicago to Chicago, then I move the thing from Chicago back to St. Louis. So Chicago holds nothing. But when you look at this thing, Chicago is a destination, a final destination. It's not a transit. Yes, but after this one, we'll look at the transit ones. Somebody say, I can't unmute. All right, let's go to Kofi. Kofi, unmute yourself.
Yes, sir. So still a bit on the details. When you were drawing in yours, I think you had the cost on the extreme right at the end of the line.
It doesn't matter. It can come first or you can swap, but don't put the two together.
Okay, sure.
Because when you put the two together, they become manya, especially when there are many arcs.
Well noted.
All right, so at this stage, you are ready to do your objective function. The objective function, as you know, is all Z minimization. Take note. And now you have to take all the arcs. Okay, you write the cost associated with the arc and then write the decision variable. So remember, you are always going to take the C and multiply the C with the X. The C is the coefficient. So the first coefficient is 6. So you write 6, and then you look for its corresponding decision variable, and that is X14. Remember, I'm still using the numbers. Then you do plus. You go to the next one. The next one is 8. And then you check its decision variable. Okay. This is where if you don't check carefully, it can flop. And that one is 8x15. Then you do plus. You go to the next one. The next one is 10. Okay. And that 10 is multiplying x16. So you do 10x16. Then you do plus. You go to the next node, which is Omaha. And you're going to take the 7, the 11, and the 11 and match each one against the x21, x24. So it's going to be 7x24 plus 11x25 plus 11x26. Guys, are you following? You can do the last one for me. You can do the last one, for us. Stanley, unmute yourself and talk.
Okay, sir. And so we will pick the last one, which will be 4x 3.
So keep going. I can write faster. Don't worry.
Okay. Sorry. 4x34 plus 5x35 plus 12x36.
Okay. That's how it is. So this now make up your complete objective function. Any question? Let me just allow you to unmute yourself for some of them. Those who tend to be disturbing, once I see you disturbing like that, I'll kick you out. I'll put you in because you are the ones who are the reasons why I have to unmute everybody. Yes, Daisy, ask your question. Unmute yourself.
Okay, thank you. So I wanted to ask, you said the past questions, some of them have about 40 or 30. So when we are solving it, do we solve it this way for all the 40? Or is
You
there
say when you are solving it, you will not solve. You will not be asked to solve this. You will be asked to write it, but not to solve it. It will be solved for you.
But you mentioned that the graph will be easier. Once you see the graph, you can be able to determine how everything goes.
No, I said once you see the graph, you can write the objective. You see the way I'm writing the objective, I'm picking everything from the graph. But I'm not solving it. Solving it requires that I need to get a linear programming software. You are talking about solving. Yeah, I'm not solving it. I'm formulating.
Right. Okay, thank you.
Yasin.
So when you were drawing, first of all, is there a fixed place where you should put the cost and then the decision variable? Because I realized that what you did in the graph is
somebody asked the same question, and I told them that it doesn't matter where you place either. You can swap them.
Okay.
You are not paying attention. You have to pay attention fully so that you know, because the guy asked this particular question. All right. So once you have written your objective function, then you bring subject to. So we are done with objective. Remember, the objective function is always the arc. The arc. The arc. Never forget that in the arc, the arc, the arc. That's where you pick your decision variables, the arc. The objective functions are the constraints. The nodes are the constraints. So in this case, we are going to write the number of constraints. So how many constraints are we going to write? How many different constraints? I'm cleaning this one. Kwale.
Note 6.
Okay. Let me show you how to write the first constraint. And this is very, very interesting. So pay attention. The first constraint should be the one you have the number 1 written for it. All you got to do is to look out for the arcs that are leaving it. Because remember, this is a sending node, supply node. So look for the arcs that are leaving it. And if it is a receiving node, look for the arcs that are coming to it. That's how you formulate. So as an example, the first one, it is, by the way, before you do this, you must remember or not whether it's a balanced transportation or it's not a balanced transportation. You have to say that. So is it a balanced or is not a balanced transportation?
It's a balanced transportation.
What makes it balanced?
Because when, should I go ahead?
Yes, go ahead.
Because when we were drawing the decision variables, we did the total, and then on the supply we had 600, and then the demand to has 600 as total.
Good. So the total demand equals the total supply. That's it. That's why it's a balanced transportation. And since it's a balanced transportation, all the constraints must have what symbol? We said that one too. All the constraints
Equal to.
must have what symbol? Because I allowed you now to talk. Okay. Some people have raised their hands. You don't let them talk at all. Okay. You know, like those people who talk at those one answer, be tomu trim pe. Then that one sharp, 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 sharp. All right. So you're going to apply the equality sign. So for the first one, you're going to write the acts that are leaving number one. And the first one is x14 plus the next one is, this is the first one, this is the second one, and this is the third one. So second one is x15. And the next one is x16. Then after that, you write equal to, because we know they are all going to be equal to. Then you write the supply, and that is 150. That is how you write the first constraint. Who can write the second constraint for us? Who can read the second constraint? Atta.
Look, the second one would be x24.
Continue. Just keep going.
x24 plus x25 plus x26 equal to 175.
Equals to 175. Good. Who can do the third one? Don't be cheating. No. Just do the right thing. Who can do the third one for us? Kelvin.
Okay, the third one is x34 plus x35 plus x36 equals 275.
Very good. Who can do the fourth one for us? The fourth constraint. I will expect some numbers to go down. Be careful. Benodai.
So I have x14 plus x24 plus x34 equal to 200.
Very good. Excellent. That's it. Now, who can give you the fifth one? Remember, you are just looking at the arcs that are coming into that circle. If you've done it well, you should see it with your eye. Cletus.
Yes.
Okay, you have x24 plus s25 plus s26 is equal to 100.
Are you sure? X24. Is that what you said?
Yes, Prof. Plus S25 plus S26.
Is that correct? No.
No.
That's wrong. If you should do it like this, you'll be marked down. So that's wrong. Who can take us through this properly? Nana Bukwame. Start. I can't hear you.
Hello, sir. So
Oh, I can't hear you. I can't hear you at all.
Hello, sir. Sir, can you hear me? Hello? Somebody else.
Okay, plenty like that.
Hello, sir.
Yeah, go ahead.
So x15 plus x25 plus x35 is equals to 100.
Okay, good. And the last one? I'm going through this thing step by step so that you don't, Davida, you don't say that it wasn't done.
Hi, Prof.
Go ahead.
X16 plus X26 plus X36 is equal to 300.
Very good. We are done with the constraint. There's one more constraint to add. Who can tell us? How do you write a non-negativity constraint here? How do you write it? Stanley.
Then that would be as usual x ij is greater or equal to 0.
Okay, good. So this is it, and that will give you your complete constraint. Okay. Now, I'm just going to show you how the overall constraint will look like. The guy who was disturbing, I've just dropped him to the place for waiting because I don't know why people can't pay attention like that. You see, I'm regulating everybody. I'm muting myself, muting people, lowering hands, increase, and things like that. And then I'm doing all of that while I'm teaching. They can't do it. They can't just regulate themselves. Okay. Ben, you have a question? If you don't have a question, go ahead.
Yes, I have a question.
Mm-hmm.
With a non-negativity constraint, since it's a balance, transportation, why do you have them greater or equal to 0?
Oh, the greater or equal to 0 is about the decision variable.
Okay.
It's not about the general constraint. The greater is about the decision variable. We are only writing it, but Excel automatically even says it should be there. Just don't forget that this non-negativity constraint is standard. It has nothing to do with the whatever constraint you have indicated. Think practical, not only mathematical. This is practical. It's practical that the number of items you are moving from Kansas City should not be negative. It's practical that way. Okay. Now, if you check, this was a balanced transportation. That's why we have the whole thing as it is. Okay. And you can see clearly that these are all of the complete model that we have. If you do it like this, you got 9 marks beautifully. But what if demand was more than supply? Then you have an unbalanced transportation. Let's say that Cincinnati is raised, the amount of tons, in Cincinnati, they are looking for 350 tons of wheat and not 300. What happens now to the totals? You see that the total demand will be 650, the total supply will be 600. We now have an unbalanced transportation. So what happens to the constraint? And here's the rule. Yes, I've seen your question.
Please, I'm trying to understand why we do the demand and supply as like notes, because it may be you can supply 150 but someone wants 200. Isn't the constraint only the demand side? I'm asking because of like how when we're doing the constraints, after we did the supply side, we have to take it from the demand side as well.
Yes, we have to take it from the demand side because what is being demanded is different from what is being supplied by individual people.
Okay.
You are supplying 150, but I don't want 150. I mean, think about those who supply things to the, what do you call it, to the provision store. Today you want how many bags of water? I want 50 bags of water. Okay. Now you come the next day, Auntie, how many bags of water do you want? She's demanding, the first time she demanded 50, now says, I want 100. Hey, Auntie, why? Because he's expecting somebody to come and take some water for some wedding. So demand changes, supply changes. They are not static. Okay, so what you are supplying is not the same as what the person is demanding. Yeah. So that is why the numbers are not the same. There's no problem with that part. There's no problem with that part. Okay. So now, if the total demand is more than total supply by 50, we have an unbalanced transportation. And that would change one of the constraints. Which constraint will change? Here is a clue. check it. If total demand is more, it is the demand one that should be less than or equal to. Write this down. The source and the destination, whichever has more of the total, that one should have the less than or equal to. So if supply is rather more than demand, suppose supply is 800, demand is 600. It is a supply one, these first three. The first three are the supply. It is this supply, they will rather have to be less than or equal to because they are more. Okay, but in this case, this one is 650 and this one is 600. So in this case, demand is more. So demand should have the less than or equal to. Go and find out the intuition behind that because it's very intuitive. But at least I've given you the sort of rule for that. Okay. Let's move on. So we've done the formulation completely. Now, so I've put that conclusion here. Angela.
Doc, please, can you take it again?
Whatever I should take it again is in the second bullet here.
Equation.
Can you write the second bullet? Write the second bullet on your screen. Write it down in your book.
Okay, thank you.
All right. So now we are ready to look at some few things. Then the first quick thing we want to look at is called prohibited route. Sometimes you are asked a question on this. The question is very simple. What are prohibited routes? And what should we do about them in linear programming? That's it. Prohibited routes are routes where it's not possible to use certain routes. So prohibited routes are routes where it is not possible to use them in a transportation problem. A practical example of a route that can be a prohibited route is when that road is blocked, prohibited because of road construction, bad weather conditions, strike, unexpected flood, local traffic laws, demonstrations, and things like that. Such a route, if you try and use it, you'll struggle. So how do you incorporate that struggle, the fact that you struggle if you use that route into the model? Well, this is how we handle it. You will assign a very large cost. You see, the costs we have been using today are just 3, 4, 5, 12, 8, and things like that. But then, because that route is prohibited, you will assign an infinite cost, or 1 billion. So when you write the model, if that particular decision variable is x29, okay, you bring a cost in front of it, say 2 billion. And that will make it impossible for that route to be used. Because the objective is to, ensure that nobody uses that route. And to make anybody use that route, you put a high cost. Now, this high cost means that if you force and the bridge is destroyed and you're forced to go through it, you can die. That's a cost. You can have an accident, that's cost, and things like that. So that is how you handle prohibited route. Belinda.
So, I was thinking, since it's prohibited, that means we are not using the route. Is it that we have an alternative route that we intend to use, or we are not going to that particular destination at all?
You're not going there at all. If you want, it's a route we are measuring. So if you have another route to use, fine. But this very route has been blocked. It's been blocked. You see it. They've written on the road, no way. Sometimes you are walking and then you go to a place, they say, no way. You say, oh, I'll go. You go there, no, you come to see that there's a big wall. You can't even climb. Now what do? You return. The route was your punishment. The cost you have incurred is wasting your time to go. That's the cost. Sometimes when it is raining, okay. In fact, just yesterday I was trying to drive. Then a certain guy, the traffic light is not our turn, but he's going to the other lane. So he still wants us to forcibly go. But there's no pathway. So he decided to just pass on my left. That is take the road where the opposing cars are coming from. And the moment he just turned and bypassed me, the two cars came and he met them. But because he's bypassed me, other cars have also what? Blocked behind me. So he can't come and enter. And they were pushing him. Guess what? These two cars were pushing. One was articulator. He pushed him to the back. Prohibited route. He has been prohibited. He still wanted to. So that's a cost associated with using a prohibited route. Okay. Now, in linear programming, you can just delete it, or you can assign a huge cost, to it. Let's go to our model. We are going to do the model right now together. Okay. I normally didn't want to do, but I did it for the other group. So I thought, let me do it for you guys too. So we are going to go into this, and then, oh, come on, where is it? We are going to just do the whole work in Excel. Yes, Yasmin.
Please, for the unbalanced model, is there a situation where we'll ever use greater than or equal to? Because in the beginning, you mentioned that
Yes,
for
there is a
unbalanced
situation.
model. Okay, thank you. And for this network model, is it always a cost minimization problem?
No, it can be a maximization. You can maximize, audience. You can maximize. So it's not always minimization. The same way linear programming is not always maximization.
Okay, thank you.
All right. So I want you to look at this. We are going to label this and just call it labels. So the first one, I want you to check. Check. In fact, normally you should have the model with you, like I have it here. And what I want us to do is to label them. Okay. We have them as X1, X2, and things like that. So let's start with this. We have X1, 4. That was the first one. Okay. Then the second one was X1, 5, if you can remember. Then you had X1, 6. Then you had X2, 2, 4. Do you remember?
Yes, let me mention this for X25, X26, X34, X35, X36.
Yeah, those were the decision variables. You're going to put zeros under each one of them. Okay. Zeros under each one of them like this. So we call this left side DV for the decision variables. And below that, you call COS EV for the coefficient. Each one of them had a coefficient. So you can see it here. You have 6, 8, 10. So that's the first one. So I'm going to write 6, 8, 10. What was the next number?
7, 11, 11.
7, 11, 11. Next.
4, 5, 12.
Okay. Now we are ready to put in our Z function. I'm going to put the Z function here. Yes, Michael.
So please, under X15, it's written 9 instead of 8.
Okay. So that's 8 here. You write equal to, and then you will select all the coefficients. In fact, you will use something called sum product. And this time I want to change the way I used to use. So you write sum product, it will pop. Then double click, then select all the coefficients. Okay, do a comma, and then select the decision variables, which you don't know now. Okay, and then after that, do F4 key to bring $1 for the decision variables, because we shall use them for the other ones. Very good. Next, you can now have the constraint. Let's call this one constraints. And then below the constraint, the first constraint, if you check it, you see it here. It is the 1, 4, 1, 5, 1, 6. Okay, so that is these ones. And the values in front of the constraint here are how many? What numbers are in front here? What are the coefficients for them?
1.
It's 1. So this is 1, 1, 1. Okay, that is for the first constraint. And the right-hand side, so here, let's go here. And then under this, write here, left-hand side, and the right sign, and then right-hand side. Okay. Now, the right-hand side for this, I'm just highlighting for you to see, was 150. So for this right-hand side, you write 150. It's an equality symbol. Check here. Always your eye should be here. Okay. It is equality. So just do under the sign, do a dot, and do equal to sign. In fact, all of them are going to be equal to, so just go through all of them like this. And let's write the right-hand side for the other ones. 175, 275. So you do 175 here, you do 275 here.
200. The next one is 200.
Then,
100 and 300.
okay. So that means that we don't need this last one here. Now, the next one is, when you look at them, all of them have got 1, 1, 1, 1, 1, 1 in front. Okay. So you're going to pick this one. You come to the next one. The next one will be for this. Okay. The next one will be for this. You check. They follow that same order. Those were the supply. Now let's go to the demand and check carefully the demand. It is X14, X24. So that one, the way the one is different. X14, okay? So that one here will be 1. But the next one is not direct. It's X24. So that's this one, 1. Then the next one is X34. That's 1. Now at this stage, I can copy this one and just paste them in the right order. Okay, you just leave one step and paste them in the right order. You just leave one step. This is it. So watch it. You are all diagonally arranged. If you check it carefully, they are all diagonally arranged. Okay. I'm trying to save transportation. Yes, ask your question, Matt Stanley.
Yes, sir. I was just asking, since the way it is scattered, perhaps if I should put them in like a table form, would
Any
it
way you want to
distract?
put it, that will help you is great.
Okay.
Now
Thanks.
here, at this section here, okay, let me just highlight. We have defined a formula. As you can see, this is a formula. Okay, so you can just copy this formula and paste it here because it's just using the usual one. And just drag it as always. And then when you double click on one, you see that it is actually picking the decision variables like we always do. So that is fine. You're done. You're done. Formulation is done. Now let's see the results. To get the results, you click on Data tab on the far right, on the top. And then on the far right, you click on Solver. So let's click on Solver. And then at Objective, you select this one, the Z value here. Okay. Then by changing cells, remember to check minimization. This is not maximization. Okay, minimization. Click on by changing variable cells. And then here, come and select all the zeros, the decision variables. Good. Now you're left with the constraint. So click Add. On the left-hand side, select all the zeros here under the left-hand side constraint. Ensure you have selected the equality symbol. Go to the right-hand side, select the 150 all the way to the 300. Click OK. And then select Simplex LP, Simplex Linear Programming. You are done. Click Solve. You are done. Click Restore Original Values. You are done. Click Sensitivity and click OK. A new sensitivity report to be created here. Let's check it. This is your final result. Let me just show you this one. So what does this mean? Look at the final value. The final value actually means that, who can tell me what it means? That, forget about the zeros. That's what it first of all means. Okay. And then only transport 25 from Kansas City to Chicago. Kansas City is number 1. Chicago is number 4. Send only 25. Now let me show you something interesting. If you can remember the original, See, the original Kansas City had what? 150. Chicago is having 200. But Kansas City didn't send everything from Kansas City to Chicago, even though Chicago wanted more. Kansas City didn't even send all of what it wanted. Kansas City only sent 25. This is you are trying to minimize cost because every item that go has its corresponding cost. So Kansas City sent only 25 to that. That is what the optimal solution is saying. And then if you check carefully, Omaha never sent anything. It had 175. It could have topped it up with St. Louis. Look at it. Okay, this is from Kansas City to St. Louis. So after sending the 25 to Chicago, we thought that it will send the other 130 to St. Louis. It didn't. Look, St. Louis is 0. Yeah. St. Louis is 0. So what did it do? It sent the rest of the 125, all of them to Cincinnati. Because remember, you are minimizing cost across all your demand and supply. So the optimum solution is for you to send 25 tons from Kansas City to Chicago, okay, 125 tons from Kansas City to Cincinnati. Okay, you send 175 tons from Omaha to number 6, which is Cincinnati. And then from DM to Cincinnati, then from DM to St. Louis, and then the rest, nothing. This is what the optimal solution is. Anyway, once you have this optimal solution, you are asked some questions. Remember, you're not going to be the one to work it out, but it will work for you, and then you are asked some questions. So let's look at some of the first questions. We've already answered the first question. Okay, it says that your mathematical model was solved. Use it to answer. Yes, Jesse.
Yeah, so just to confirm. So the process that we just went through is very similar to
I can't hear you.
can you hear me now?
Uh-huh.
Yeah. So I was just asking to confirm that what we just went through on this exercise is very similar to how the linear program is.
Yes. So the question says, what is the optimal solution? So this one, you type it. I just said it. The optimal solution is to send 25 tons from Kansas City to Chicago. And let me pick the last one. And to send 100 tons of wheat from DM to St. Louis. So that write-up is here. Okay, 25 from Kansas City to Chicago, 100 from DM to St. Louis. You type it all. The next one is to draw. Draw it. So you're going to redraw the whole thing. You go back and keep your circles as it is. But this time, you are only going to show those that have what? Positive values at the final value. Just use those ones alone to draw. You track them. X14, you draw it. X1. So whichever one that has got an arc, you draw it and add the cost. You draw it and add the cost. You draw it and add the cost. And this is your new drawing. Next. Yes, Yasin.
You kept saying that you draw it and add the cost, but these ones are not the cost, right? They are like what
Sorry. You draw it and add the decision variables.
Okay.
The next part of the question says, what is the total cost corresponding to the optimal solution? What is the total cost corresponding to the optimal solution? Who can show us how to answer that? What is the total cost corresponding to the optimal solution? Okay. Now you'll be able to use the final value and something to help you get that. What do you use? What do you use? Benoda?
The objective coefficient.
What do you do? Give me an example.
You multiply the final value by the objective
Show me an
coefficient.
example.
So the first one, so cell, let's say B2, you multiply the 6 by the 25 plus, since the final value for the next one is 0, we can leave that one out. Then we multiply the 125 plus 125 times 10 plus the next one is 175 by 11 plus 175 by 4 plus 100 by 5.
Very good.
Yes.
That's how you execute it. This is exactly how you got to execute it. Now, once you do that and you do that well, you're going to get 4,525. This is it. Okay. Now, there are other questions that I can ask you, okay, or you can be asked. For example, if you check very carefully, the reduced cost for the first one, which is Kansas City to St. Louis, is 0. Okay. The reduced cost, sorry, is 1. Okay. Why are the reduced costs, aside those that are 0, why are the reduced costs all positive? Why are the reduced costs all positive? Yasin.
Because we are dealing with a minimization problem.
Exactly. Because we are doing a minimization, and in such a case, you should have a reduced cost of positive. Now, what does a reduced cost of 1 for Kansas City to St. Louis mean? 1.5, x 1.5. What does that mean? You can ask that question, okay? Then the next question I could have asked is, if you check, for example, the constraint side, okay? If you check a constraint side, all the constraints are balanced. Okay, the left-hand side, they are all binding constraint. The left-hand side equals the right-hand side. But we said something about binding constraint. Do you remember what we said about binding constraint? Yeah, Nagoli.
Doc, that the shadow price are positive when the constraints are binding.
No, we didn't say the shadow price are positive when they are positive only in the maximization, but the shadow price can be positive or negative. You get a point? In other words, we said the shadow price are non-zero. The shadow price are non-zero. But this one, the shadow price are some of the shadow price are 0. And of course, some are also negative. Think about what it means. Okay. If you increase any 1 ton, okay, 1 ton to go to handle the demand constraint or the supply constraint or any of the demand for those that are there, the shadow price will tell you how much profit will go down or how much profit will rise. Now you can see that for some of them, it's telling you that the profit, the cost will fall. Some of them, if the cost fall is good, isn't it? If the cost fall is good. So if I were to ask you that which of these constraints is the most critical, source of constraint, what would you say? Which of these constraints is the most critical source of constraint? Oda.
So it will be the K8 and K9. That's all K8 and K9.
You have to choose.
Then I'll choose a cell K8.
That's what you should have chosen.
Okay.
The way you're saying K8, as if one is not better than the other, but one is better than the other. So that's what I mean. You can have multiple questions related to this. You're done. Let's go to the next model. We can extend the transportation model to a transshipment model. Kofi?
Yes, sir. I wanted to know if for where we have the decision variables being 0, do they become forbidden routes?
Would they be what?
Do they become forbidden routes from the sensitivity report?
No.
Okay.
They won't. The forbidden routes are very, very carefully done. No, they are not done here. Okay, so we can add a transshipment node to the between the supply and the demand nodes. Okay. A transshipment node is a node that connects the supply and the demand. It sits between the destination and the source. Now, watch it about transshipment node is that they don't have anything they keep. Write it down somewhere. They don't have anything they keep. They don't keep anything. They don't keep anything. Because whatever comes to them, they also send it. They are not like their demand. Demand, whatever comes to them stays. They are not like supply. Supply, whatever is with them goes. But the transshipment, they get it and they give it out. They get it and they give it out. Now let's continue our model. You know, we had the 3 grain elevators in Kansas City, Omaha, and DM. They were storing the grains, the wheat grain. But what we didn't tell you earlier is that before the grains were stored in these 3 cities, they were actually harvested at farms in Nebraska and Colorado. That we didn't mention. Now we are telling you that Nebraska and Colorado, that is where the farms are. So the items, the wheat, are actually transported from the farms to the grain elevators. Before they are from the grain elevators, they go to the final destination, which in this case is the supply, the demand. So at this stage, now that we have brought the whole thing to that level, so you can see that in the new cost, we have the cost of transporting it from the farm, which is in Nebraska and Colorado, to the 3 cities in Kansas, Omaha, and there. The question now is, how does this change the number of constraints? Who can tell us? How does this change the number of constraints? Previously, the number of constraints were 6. What would that be now? What would that be? There were 6 before. Calvin?
They will increase.
Sorry?
They will increase.
Hey, Master, you want me to tell you? I want to tell you that you mean that we all don't know the increase. Yasin.
Please, it will become 3 because now the Kansas City, Omaha, and Des Moines will now be just transit places because they don't actually receive anything. So
So
it's
what
like,
happens? So what happens to your constraint? You said it will become 3.
yes,
Okay.
because it's like you are moving from, let's say, Nebraska, but the final destination is Chicago, but it will just pass through Kansas City. So Kansas City, Omaha, and the
Everything
last
is
one.
important. You know, when I was showing you the picture, everything is important. Everything matters. Ben.
That'll become 8.
It will become 8.
Yes.
Yeah. It will become 8. Sometimes people learn from people's mistakes. Maybe if Ben had answered it first time, he wouldn't have said 8.
So I had 8 in mind already, you say.
But you didn't raise your hand before until 2 people spoke. Yeah.
Said 2 marks.
No. That's a different ball game because I knew you had it. So why would you wait for them to? You didn't have it. You were also thinking like they were. Yes.
So are we saying it's 8 because now Nebraska and Colorado will become nodes?
Yes. They are going to be nodes. Because remember that those grains came from their farms. They are part of the network. Everybody is part of the network. Yeah.
You see, you mentioned that the nodes are the constraints. So in
Yes.
this case, is it that we are using the constraints or like the point at which like the items pass through? Because I'm wondering if it's a constraint, how is the source a constraint? Like
But all
Nebraska.
along, the source had always been a constraint. When Kansas City was a source, where it started from, it was a constraint. And if you can remember, we always say that there are supply constraints and demand constraints. The only thing is that now we have a transshipment constraint because they are transshipment nodes. As long as you are a node, you are a constraint.
Okay.
So if I were to draw the things, I'll have 1, 2 for Nebraska and Colorado. Then I'll have 3, 4, 5. Okay. Where the 3 is Kansas City, you have Omaha, and then you have the DM. And then finally, the usual demand one, Chicago, which is now 6. And then you have the next one, which is St. Louis. And finally, you have the Cincinnati, Almaty, Cincinnati. So this become the nodes now. And now you need to draw it. Now watch how you do the drawing. This will be X13, isn't it? Do you agree with that?
Yes, Doc.
Yeah. And what to be the cost? We are talking about Nebraska to Kansas. It's right on the screen.
16.
16.
Good. So you have 16 here. Okay. And then the next one will go here. Okay. I'm just using coloring to just distinguish. Then this, no. So you start, this one will go here and this one will go here. This will be 16 and then you have X13. And then the other one will be 15. Actually, you need a third one. The other one will be 10. Okay. And then you have X14. And the last one will be 12. And you have X15. And you do the same thing for the number 2. But let's go to number 3. Suppose you are from 3 going. The 3 will go to 6. The 3 will go to 7. The 3 will go to 8. Okay. And there's a cost for that. Because don't forget that these 3 already, their costs was something we had from the previous question. Okay. So you give them each of, but the labeling will change because this one is going to be X36, X37, X38. Like that. And then the rest will follow and follow and follow in your drawing. So if you draw it well, your actual drawing is going to incorporate the previous ones. You're going to have something like this. But you can see now how plenty is becoming gradually. Of course, you and I both know where it came from, so don't worry. Nine marks. 9 marks. Okay. Once you have drawn, look at the next part of the question. It says first, define the decision variables. Again, the decision variable will be the same thing that we've been doing. Okay. Let Xij be the items or the number of tons of wheat transported from node I to node J. Develop a network graph. We've done that. Formulate the model. Now we are ready to formulate the model. And in the formulation of the model, your eye should be on the X. The X. This is still a minimization. So you write Z min. And then you take the first one. The first one is what? 16 and then X13. So you write 16 X13. Followed by 10 X14. 10 X14. Okay, followed by 12. So you do 12 X15. So I just did this 16, okay? I did this 10 and I did this 12, okay? And took their numbers here. I'm sure you can do the rest. In fact, when you finish, do 1, 2, and 3, okay? When you come here, you are still going to count this one, okay? So this one here, this one at the top here is going to be, let's say you've done it up to that. You do plus X36 plus X37. x3 7. And then it continues on and on and on. So I just took this one, which wasn't written, and I took this one. And then the last one for that level will be this. Then you come to number 4 and then keep going and keep going again. I hope you guys are following. If you should do that correctly, you should be able to get something like this. This is a complete model. But we are not scared because we know where we come from. That's it. Where you are is fine, but where you are going is more powerful. Yes, sir.
Please, when you were doing from the, if you can go to the slide before, from the 3 to node 6, you did it x3 6, but you didn't add the cost of 6. I don't know if
Where is it?
the slide before this one.
Let's see. These ones?
Yes. No, the other one, the white one. Yeah.
Yeah, this
The
one, I
white.
didn't add the decision variables because I took it from another book. And they just wanted to not keep the thing ugly. So they didn't include the decision variables. It doesn't mean that she didn't include it.
I meant when you were actually saying the what we should put in the z function, you didn't include the costs, and you just did x3 6.
Where is that?
Plus,
Where did I write that?
So I
on the
think the
white.
slide after this one, the diagram for this
Show
one,
me.
the other one before this one.
Before,
Before
yes,
this
this one.
one.
When you were asking we should do from node 3 to node 6, you said x3 6, but I didn't hear you include
It
the
was written.
$6.
It was written. I had it earlier in a PowerPoint, but I think that when I was bringing it to the PDF, it did not capture that very box. You know, when you do it in PowerPoint, it didn't. But we all both knew that it is supposed to be there. That's why I mentioned it naturally. Okay. So now that you've done your objective function, you're left to the constraint. Now, this was a balanced transportation model and it's still balanced. You have 600 on the left. Okay. And then you have 600 here as well. So it's still balanced. So now what do? We know that everything is going to be equal to. Okay. Now, how do you do the writing? We know that if you were to write the constraint for Nebraska, okay, it's going to be what? It's going to be x13 plus x14 plus x15 equal to 300. Do you agree with that?
Yes, Doc.
Okay, but nobody should ask me, why is it negative 300 and I've written 300? Because everything, not only... Sorry? Okay. So that is for that one. Now let's look at the second one. The second one we can easily do. But I'm interested in the third one, the transshipment. This is how you calculate the transshipment constraint or node. You count the number of arcs that are entering into it. So be clear and tell me which arcs are coming into it and which arcs are leaving it, because the principle is that they got to be equal. So how many arcs are coming to it? If you check here, you see that x13 is coming into it. Plus, you go to the next one, x23 is coming into it. Okay. And this should be equal to what is leaving it. The first one that is leaving it is x3, 4, followed by x4, oh, sorry, it's x3, 6. Okay, followed by x4, 6, followed by x5, 6. So you see the way I've written the constraint. You just pick the arc that are coming into it and equate it to the arc leaving it. You see?
What you said x4 6? Isn't it supposed
You sound
to be
far away.
You said x4 6. Isn't it supposed to be X37 and then X38? The ones that are leaving.
Oh, yes, it's true. So let me just rewrite that. So you have the first one here, which is X36. Then you have X37. It's actually 37. And then the last one is X38. That is a third constraint. The fourth constraint, who can tell me how the four constraints should be? I mean, you can do it. You just take this one, X46, X47, X48. And that is how you get a fourth constraint and all of that. So if you are to do these constraints quite well, if you are to master them, you're going to get something like this. Remember, when it is equal to, I move all of them to the left-hand side, then it becomes equal to 0. So all that was, these ones were on the right-hand side here. They were positive. Then I brought them to the left. They became negative. Yes, Daisy.
So you said we shouldn't ask you about the minus 300, but can you kindly explain why the 300 is minus?
Okay, the 300, the minus sign is not only given to the 300, but it's given to all the variables that are on the left as well. The minus is simply indicating that the thing is leaving the system. So we are just using it for beautification. The thing is leaving. So leaving makes it what? Minus. Coming makes it plus. So when the items are coming, so you see that most of the supply, because they are leaving, most of supply will use the word minuses. But the thing is that in the linear programming, if you check this thing carefully, the minuses will cancel, isn't it? That's why I tend to use the plus straight on. But sometimes, it's good to understand. It's just for cosmetic purposes to indicate that they are leaving. Daisy, do you get it?
Okay. Yes, I understand. But within the graph, the first one was minus, the second one was positive.
Again, it was
But
a
over
typo.
here,
It was a typo when I was copying it to my PDF.
okay.
Yeah.
Thank you.
Now, when I clear this thing, of course, you can do this thing as well in Excel. I don't want to do it, but I'm more interested in the result that you get. So this was the result. Everything after this is the result that you get. I want you to look at the results because in some of the questions, they don't ask you some questions like what is the optimal solution and blah, 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 blah. No. What they would rather ask you is to write the Excel formula that generated what you have. Excel formula that generated what you have. So let's look at the first question. What formula was typed in cell I11 for the total cost? What formula was typed here? I11. Now, first of all, the Excel that was obtained, they've rearranged this. So the cells are cell A all the way to J. Okay, and then the rows are from all the way 1 to 16. And this is the result, actually, the Excel result. And there is a cost here, but you remove the cost, and it's asking you to indicate the formula that generated the cost. Well, that shouldn't be difficult because we already know the formula. Don't you know? The formula is taking each of the decision variables and multiply it by coefficient, isn't it?
Yes.
Okay, so you take each decision
Yes, sir.
variable
Yes,
and
sir.
multiply it by the coefficient. Okay, now the coefficients are those here. So these are all the coefficients. So because these are all the coefficients, you have the decision variables also here. So all you got to do is that you can use the sum product. You can say equals to the sum product of whatever is from A2 to A16. Okay, A2 to A16. And then you do a comma. Remember, 82 to 860 means you're going to drag it. Okay. And then you have to put a dollar symbol if you want to replicate. Now, this one is not too key because the formula has been generated already. So you get 82 to 816. And then you remember that you take each one multiplying the cost, each one multiplying the cost. That is what our objective function said. So you will now do comma. The cost section is what? F2 all the way to F16. That's it. F2 all the way to F16. So you do a sum product of the first one and that of the second one. Sum product here means that you take the 16 that is here. Let me just delete all this. Okay. You take this 16, you're going to multiply it by this Xij. You take the 10, you're going to multiply it by this Xij. You take the 12, multiply by this Xij. And that is how it is. That's how it is. So let's see the answer for that. So that's it. A2, A16, okay, F2, F16, sum product. Next question. What formula were typed in cell I2 to I9? Yes, Stanley.
So, which mine was a question in the previous one. Won't the cell be locked with the F4? I mean the formula. Would you have to add that?
Yeah, you can add that, to be honest with you. But the thing is that for this very one, you may not add that because we don't know what it is going to be locked with. You know. Because, but if you add that, it's not a crime at all. So you can.
Thanks.
So the total cost we've gotten to know, but it says what? Let me see. I2 to I19. So this column. So he's actually looking at I2 to I19 all here. But let's deal with the I2 first. What formula was there? What formula? You start with equal to. What formula gave us the I2? Now look at the I2. It's the left-hand side. Remember, he applied negative to all of them, so it's maintained. It's the left-hand side of the equation. Now, if we check our own formulation here, if we check our formulation, it's the left-hand side where I've highlighted. So it's actually talking about this thing. So the formula there is the same, product if it was formulated by like our own. But I want to show you an easy way in case that you didn't even use some product. So let's take this one here, negative, okay, negative 300. How did we get this? Well, check, yes.
Please, we use the source and demand, like quantity in that was given in the question.
You said that what we used was not in the question.
No, I'm saying for like I2, we picked what was in the question. So like the negative 300 was what Nebraska was going to like transfer to the other state.
Yeah, I don't get what you mean, but whatever
So
it
like,
is.
yeah, asking that what formula did we use for I2 to I9?
And are you giving the formula?
So like what I'm trying to say is that the formula is that we picked it from the question.
No, you can't pick it from. You can't pick it from the question because this is a paper in front of you.
Okay.
So what you do is to get this one, check the formulated model. Is that what you meant?
Yeah, because in the question, like I saw that okay, so I should have said the formulated model. Okay.
Yeah, you check the formulated model and go check the formulated model here. You see that at this formulated model, the first one is a 300. What led to the 300? Check it carefully. You had X13, X14, X15. X13, let's go back here. Oh, here. X13, that's this one. Okay, X13 is Nebraska, if you can remember. This is it. X13. That's Nebraska. Okay, and we are looking at Nebraska's item that was shipped here. So to get this formula, because it's also negative, you would just say that negative, remember, you're going to add and multiply. So it's going to be 1, okay, 1 multiplying that cell. But the 1 is a coefficient. So the question is that, where is that coefficient of 1? And by the way, take note that it's not from the from. But once you have the thing, it's already a coefficient of 1. So there's no problem with it. So we put it there. So you will have this cell, which is A2. So you have negative A2. Okay. And then, because the negative A2 is the actual actual values that were shipped. So negative A2 minus, the next one is negative or minus A3 minus, the last one is what? The last one is A4. Okay. So the formula that I actually put here is that. But going back to the question that my good friend asked, this is where you can also bring the, what do you call it? The dollar symbol equation that we used. But I'm just giving you a simple one here. Okay. So the simple one here means that if you take this one, that one, and this one, okay, the rule is that it shouldn't be less than, it should be equal to 300. And actually, when you add them, they're going to be equal to negative 300. Okay, so that's how you got to execute this one. Now, for the next one, they say you should copy it and paste it. You can just say that the same thing can be repeated by changing this one. So let's go to the next one. The next one is what? This very one. So once again, to do that, check the model. Oh. Let me just go up to check the model. Oh. Am I on the right this thing? This one. Can't even see where I was before.
I think page 442.
442. Okay. So when you look here, okay, and you're trying to work out this very example here, you're supposed to have the second one, which is this 300. And you're supposed to check this model. Okay. Come on. So look at the model. You have 2, 3, 2, 4, 2, 5. Okay. 2, 3, 2, 4, 2, 5. So that's what you're coming to pick here. Where is the 2? They are down here. This one here is going to be 2, 3. This one here is going to be 2, 4. And this one here. So the cell name are A, A5, A6, A7. Okay. So you take minus, you write minus A5, minus A6, minus A7. That's it. And that is the formula that you need to be able to get whatever you want to get. You are summing the element in there. So the moment the elements come now, you see them reflecting on that side. That's it. Then when you go to the ones that are 0, okay, you do that for that. You write the formula. All of these things means that you have to write all of the 8 different, constraint formula, Excel constraint formula. Yes, Yasin.
Please, I'm wondering why we are using negative because me when I enter it, it doesn't give me the 300 at the Colorado side. It gives me negative 600. So is there a reason why we use negative?
Gives you what?
Negative 600. If I do the A5, A6, and A7. Ah, okay. I think I've seen my mistake.
Yeah, you've seen your mistake. All right. So that's all you got to do, and the rest will follow just as it is. This is just to tell you that there are some times where you have to deal with only formulae and not this thing. You won't do it in Excel, but they will ask you the question as if you were doing in Excel, what formula will you write? For example, I always say do the $sign out of that. Those things you can be asked. Yes, Yasin.
So when we are doing the formula, that means there can be situations where in our formula we'll use the positive sign, right?
Say it again.
When we are like writing out the formula, sometimes there can be a situation where we have to use positive instead of the minus sign, right?
Yeah.
Okay.
The only reason I'm using these minuses is because I see that in the answer they have minus. Look here, I can see that they've written minuses. That's why I'm also going by that. Otherwise, I wouldn't bring it.
Thank you.
Now, the next thing, and then the last one we are going to look at is, so this conclusion comes from that. I think there was a question on what is optimal solution, and I think I've done it. You take each cost and then multiply it by the final value. The last one we're going to look at is assignment model. It's the easiest of all. It's the easiest of all. What is the assignment model? Okay, so look at this. You have been told that there is a conference game. The conference game is like basketball game. Okay, and it is being played in 3 different towns. 4 different towns. And you have officials who regulate the game. And this model that you have here, you have officials that will go here. So I want you to watch something. These are the game sites. They are in Raleigh, Atlanta, Durham, and Clemson. The number of officials have to be assigned. That's where the assignment comes in such a way that they will minimize the total distance. Okay, they will minimize the total distance. So when you look at officials A, if they want to minimize the total distance that you see there, where do they have to travel to? Officials in A. Where should they go to? They can go to Raleigh, Atlanta, Durham. Please raise your hand. Then Clemson. Where do they have to go to be able to minimize the distances available? Davida.
Hi, Atlanta and Clemson.
It can never be Atlanta and Clemson. I say officials A, where should they go to? That was a question. Mercy.
Atlanta.
Officials B, where should they go to?
Atlanta.
Emmanuel.
Oh, okay.
Atlanta.
Officials D.
Yes, Doc, Atlanta.
Samuel. Okay.
Doc, Atlanta.
So all of them will have to go to Atlanta. All right, so officials B. So if you look at this carefully, they can't all go to Atlanta, even though it looks like they should all go to Atlanta. They can't all go to Atlanta. So we got to assign them in such a way that we are minimizing total distance. So what is the first thing to do? The first thing to do is to decide in your mind what are the demand and what are the supply. The good thing about the assignment model is that the constraint will always be equal to 1. Write it down somewhere. The assignment problem, the constraints are always equal to 1. Each constraint is equal to 1. And the reason why this is because you need only one group or one official to be in one place. You can't be in multiple places at the same time. So you count how many are the supplies and how many are the demand. So how many are the supplies here? When I say supply, how many officials are we supplying to the game site? Yasmin.
Doc 4.
And then how many are the demanders? Nakule.
Doc 4.
4. So now we know that we are going to draw how many nodes? We know we are going to draw how many nodes? Nanakame?
Yeah. 8.
8. That's it. So you're going to draw the nodes in such a way that you have 1, 2, 3, 4, 5, 6, 7, 8. That's how it's going to be. Okay. And this one is from the officials in A going to Raleigh. Okay. From Raleigh. Officials from A going to Raleigh here, going to Atlanta here, going to Durham there, and going to Clemson there. And for each one, you add the distances. The distances are 210, 90, 180, and then 160. And then you do for the next one. And then you do for the next one. And you draw them very, very nicely. In fact, if you should do that perfectly, you're going to get something similar to what you have here. As for the decision variables, I've always been telling you. So you should get something like this. Belinda.
Sir, please, I wanted to understand something. Is it that all the games are happening at the same time and we need each set of officials to be at each game?
They are all happening at the same time.
Okay.
Okay, so now you've done the drawing and you need to write the objective function. It's the same thing. You would take the objective function to take the 210, multiply it by this. You take the 90, multiply it by that. You take the 180, multiply it by this. And you take the 160, multiply it by that. And then when you're done, come to the next one. Okay, so you got a 7 marks here. You come to the objective function. Let's go to the objective function. Okay, and then you get this. This objective function gives you another 7 marks there. You see, it's quite many, but you know what you're doing. That's the most important thing. So that is how you formulate the whole thing into a linear program. Now let's go to the constraint. I told you that the constraint, each one of them is equal to what?
1.
Okay. So when you look at this constraint, we can easily formulate a constraint once again from the acts that are leaving. And then you set it equal to 1. Then the acts that are entering, you set it equal to 0. So I want somebody to tell me how to formulate the ones I have circled. Okay. Officials A and Clemson, game site. Who can tell me how to formulate the constraint for official A? Just use the information that you have on your screen. The information you have on your screen. Who can tell us? Emanuela.
So XAR plus XAA plus XAB plus XAC is equal to 1.
Very good. Who can do that of Clemson? That of Clemson. Yasmin.
X XAC plus XBC plus XCC plus XDC is equal to 1.
Very good. Laban. Okay, so that's fine. So once you've been able to do this, the rest is just formulating the model in Excel. Of course, that will be done for you. And then you get this result. So let's see the result. This is a result you get. Looking at the results, you can clearly identify which officials should go to where. Which officials should go to where? Who can tell me which officials should go to where? Based on the optimization model, which officials should go to where? That's it.
Official A should go to Atlanta. Official B should go to Raleigh. Official C should go to Durham. And official D should go to Clemson.
Perfect. This is it. Now, if you force, because you are not supposed to do, if you force officials A to go to Raleigh, what will happen? If you force officials A to go to Raleigh, what will happen? Raleigh. Yes, Yasin.
You increase cost by 90. Or increase the distance by 90.
Exactly. You increase the distance by 90. Is that good or bad?
Bad.
That's it. Okay, so right now, as it stands, if you want to get your minimum distance, don't send any official from A to that of Raleigh. And then, of course, there are other questions that you could be asked in the process of this. Okay. So when you find the optimal solution that you spoke about, you can now write it in sentence that assign these officials to this group, assign that official to that city, and that's it. And then you can redraw the whole thing, this time indicating that one official's actually supposed to go to where. This is a graph that will show everything you've drawn. Now, what is the corresponding value of the objective function or the total distance corresponding to your answer in D? What is the corresponding value of the objective function? Who can walk us through how to get that? The corresponding value of the total distance. How do you find the total distance? Ben?
The final value by your objective coefficients.
Take them and let me see.
So 1 by 90 plus 1 by 100 plus 1 by 140 plus 1 by 120.
Super. That is how you address that. Then you add all of them together and you get your final answer. You should get 450. That, ladies and gentlemen, is the optimum minimum distance. And that brings us to the end of the entire Kabudo. At this stage, I'm going to take questions. If you have a question, feel free and let's enjoy.